So I need to start off this talk with a bit of a warning. This presentation does contain gratuitous fantasy and Dungeons and Dragons references, so you have been warned. And with that, we're gonna jump right in. So this talk is called Wyrcan, the Bootloader Container Saga, and we're gonna start here with Chapter 1. Hopefully, all of your character sheets have been prepared, and you are ready to play a round of Dungeons and Dragons. We're going to start off by identifying our hero. Our hero is actually not the project in this talk. It is the project called Enarx. Enarx is an open source project which runs WebAssembly workloads in trusted execution environments. Does everybody know what trusted execution environments are? Good. I am glad nobody knows except for a few over here. So the idea of a trusted execution environment is that there's a mode of the CPU which encrypts all of the pages of the memory, so for a particular application or a subset of that application, and then can do hardware-based attestation. So we can use Enarx to bring up an application in an environment that's actually encrypted while it's running, and we can prove to others that that environment is tamper-proof and encrypted, and then deliver keys and such into that, which is a great way to write microservices, because you don't actually have to rely upon the security of the underlying operating system, just the trusted execution environment platform itself. Enarx is also a Linux Foundation project within the Confidential Computing Consortium. In fact, we were the inaugural project for that division within the Linux Foundation. So let me give you a little bit of background on Enarx history. Enarx started in 2019, and it started basically by us going to Intel and AMD to explore their new technologies, Intel SGX and AMD SEV. The first commit, I think, was in February of 2019, something like that. And it was actually written in Austin, Texas, while we were talking with the developers there. And basically, the idea was, how can we make this portable? You have technologies that are on different platforms. They work in very, very different ways. How can we create trusted execution environments that are the same across all hardware platforms? And in 2019, we decided, late 2019, we decided to focus on WebAssembly. And we merged WebAssembly support in 2020, late 2020. And kernel development at this point is happening in earnest. So you have lots of patches for these new hardware technologies coming into the Linux kernel. And then in 2021, SGX, the first for version 1, lands in the Linux kernel. Version 2 is, I'm very excited about this, is about to land in the next kernel release just now. And SEV, the first version of that, began to land in the Linux kernel in 2021. And in mid-2021, my company, Profian, which is a startup we launched to provide commercial support to Enarx and to allow you to be able to deploy applications in the cloud and on the edge in ways that actually don't depend upon the security of the underlying operating system. Of course, in 2022, we're going to be releasing Profian Assure, which is our enterprise support for Enarx. But this is... Let me give you a brief demo of how Enarx works. So you can do this on your own. There's no special magic here in what I'm about to show you. You do need the latest generation of hardware in order to take advantage of the hardware capabilities. So this is Ice Lake Xeon for Intel, or the Milan generation for AMD. And since not everybody has these servers sitting in their back pocket, we decided to make a website called try.enarx.dev. And you can click Start Now, and it will randomly pick one of the platforms. We ended up with SGX in this case. And on the right-hand side of the screen, we have a small Echo server. This is written in Rust using the Qemu ISO framework. And the only thing that's WebAssembly specific in this whole application is this line, because we're going to create, or we're going to use a socket that was already set up by the runtime. And other than that, this is all just native code. So we're going to listen for new connections, which we're going to accept. When a new connection comes in, we're going to spawn a background task in Qemu, and we're going to handle its output. So we're going to read whatever the input is from that socket, and we're going to handle a disconnection, and then we're going to write it back. So a very simple standard Echo server, and we're going to build this for WebAssembly. So normally we would just do a cargo build, but since it's WebAssembly, we're going to specify the target, WASM32 WASI. And now our application is built for, oh, I think somebody's playing with the server. They just took it down. Let me try the other one. Nope. That's how you know it's a live demo. Anyway, we could have uploaded this to the server, and we could have shown it running on try.enarx.dev if it was not down. So maybe I'll come back to this at the end of the presentation, see if it's back up. Maybe somebody's deploying a new patch or something. Okay. So that's actually not what this talk is about. This talk is actually about Wyrcan. And so one of the challenging things that we had with Enarx is that we need to move on now to chapter number 2, testing your metal. And yes, I know this is a pun. I hope I didn't injure anyone. Testing your metal is, of course, spelled M-E-T-T-L-E. But the problem we have is that we need bare metal, because when we're developing this software and we want to test it rigorously, because this is security software. And so building Enarx needs bare metal. We test development kernels, we test hardware cooperating user space daemons, we do application development, and we do it on heterogeneous hardware in heterogeneous clouds. So all of the clouds basically are offering bare metal in various forms these days, but how you actually boot an operating system across all of these different clouds is incredibly different, and they're not really the same. And we had other problems as well, but this is really a many-headed dragon, as you can see Tiamat here. And so we have a variety of different ways that are in use for booting bare metal. You have the standard sort of PXE system, which is you use DHCP. It tells you the TFTP place to get your kernel in RD. It fetches those over the network and boots them. That's one way. Another way is iPXE. This is commonly used by Equinix, for example. And so iPXE is like PXE, but it's scriptable, so you can basically write some scripts to do things. And it also has like HTTPS support and stuff, so it's not just TFTP. But it sort of has TLS support, because iPXE only supports really old cipher suites. So if you actually try to download images from, say, GitHub or pretty much any modern web server, it's going to fail because it can't actually do the TLS negotiation. You also have the ISO method. Some places will allow you to upload an ISO and to boot that, which is great. Usually you'll have to go through an operating system install, so it's not really unattended, although there's ways you can sort of make that automated. Then you have the EFI direct boot route, which is where you put an EFI image on an EFI partition, and that gets loaded directly. Then you have the operating system image. This is usually a derivation of the ISO format or some other thing. There's a 3-letter cloud, for example, that requires you to have a custom image format for their servers. And then lastly, we had to mix this also with stuff on-prem. And so being able to just do like a USB mass storage boot, for example, is another way we may want to boot these things. And so because we have all of these servers doing rigorous testing of all of the hardware, and we have all of these clouds, and we have all of these different ways to boot things, we really needed a system that could sort of wrangle all of these together. So we really need to tackle that multi-headed dragon. And we have specific goals. First of all, we want our process to be iterative. And building a whole operating system image is, yes, it's iterative, but the cycle is just really long to be able to build a whole OS image. We wanted to do something that was faster, more lightweight. Second was we wanted something that was stateless. We didn't want to install an operating system and then have to manage the state of that operating system over a long period of time. We wanted to boot into an OS where everything came up with the bare metal, and then when we rebooted, it was exactly the same state as when it started before. Third was we wanted everything to be declarative. So we wanted a clear recipe to be able to build our operating system images. But we also test on multiple different operating systems. And so while, for example, we could use something like Kickstart to do an install on Fedora or Red Hat, and other systems provide other automated systems as well, that would have required us to maintain a bunch of different methods for composing these images across multiple operating systems. Fourth is we want the process to be reproducible. This is incredibly important for any development or testing environment, particularly when you're dealing with very rapid development across changing situations. You need to always be able to reproduce something at a particular point in time. So we wanted to be able to reproduce every single OS build. The fifth thing is that we want it to be homogeneous. So in other words, if we're booting an operating system, it shouldn't matter which hardware we're booting it on, and it shouldn't matter which cloud we're booting on. The entire process should be the same. And further, the development procedure for building that and booting that operating system should be the same for everyone across the line. Lastly, we wanted it to be infrastructureless. And now I know that there's not really such a thing as no infrastructure. But basically, there's a lot of infrastructure that's provided for free from a lot of different places. And we didn't want to have to set up infrastructure to manage our infrastructure. We wanted something that could be very easy and lightweight, particularly as we had a small development team. We didn't want to have to start doing IT ops immediately. And so we simply needed more agility. We needed the ability to move faster and to create environments that were reproducible and so forth. So let's move on to Chapter 3. Arming the party. We already had, as I mentioned, some resources available to us. So we start with Git, right? I mean, if you haven't heard of Git yet, you should probably go learn about it immediately. Git is pretty much the de facto way in our industry these days to manage iterative changes. And so we wanted to be able to use Git to manage the control of producing images that we could use for booting. And we wanted the whole thing to be declarative, right? So the image is produced in a declarative way from the recipe that is in Git. And this gives us those two things we really wanted, which is rapid iteration and change control. Second, we do have available CI/CD resources. There are many, many examples of this all over the web. I listed two here. We have GitHub Actions, where you can run some code on their server in the cloud on your GitHub pushes, or the same with GitLab for CI. If you tag something, if you do a push of code, whatever, you can run code on all of those events. And so this is essentially some free compute resources for us, and we wanted to make sure that we could do this efficiently. And lots of people are doing this today, right? This is a really well-worn path. Committing a Docker file, for example, and building a container in GitHub is not exactly the bleeding edge of technology. The last thing is that we have available container repos. And so basically, forges like GitHub and GitLab both have the ability to start with that Docker file that's in GitHub, do the build of the Docker image, and then push it into a container repo. And now it's actually staged for deployment. And so we didn't want to introduce additional infrastructure on top of this. We just wanted to say, like, look, we've got our whole operating system packaged as a container in that container repo. I just want to boot the dang thing. How can I get it to boot? And so there's an easy part of this and there's a hard part of this. The easy part of this is actually distributing the kernel in initRD. Because if you look at a container image, it's basically a set of layers. It's a set of tarballs that are layered and contains all the changes you've made to a container over time. And we can stuff things in this and then we can distribute this, right? Typically, you don't distribute a kernel in initRMFS in a container because it's not going to use that kernel for anything, and it would bloat the size of the container. So we needed a way to do that. And that's really easy, actually. You just kind of install the distro's kernel package. That's an easy step out of the box. There's a few other little tweaks you have to do, but it's not very difficult. The second part was the harder part. And that's container-aware bootloader. So we needed something that could start up on the system no matter what boot process we had, right? Whether we were doing iPXE, whether we're doing native boot, whether we're booting off an ISO or whatever. We needed some bit of code there that could recognize how to get a container image and then figure out a way to actually boot that kernel. And so we came up with the idea to make containers more metal. And we started a project called Wyrcan. Wyrcan is available on GitLab, so gitlab.com/Wyrcan/Wyrcan. And it's written in Rust, and I believe it's under the Apache 2 license. And this is the bit of code that does that harder part in the early part of the bootstrapping process. Wyrcan provides these four things. These are the main things. There's a few other things it does, but these are the main four things that it does. First is it does container muxing. It basically takes a bunch of different container layers from a container repository, starts downloading all of those. It downloads them in order as they would be actually laid out on the file system when the layering was collapsed. And we stream this whole process. So we're actually untarring them as they're downloaded, and then we stream it into an initRD image. So we actually convert the Docker format into an initRD format. One of the other things we need to do as part of this process is we need to actually extract the kernel from this image. Because although we can boot the initRMFS, we need to get the kernel out separately to be able to handle that. So when we do the container muxing, basically we're just grabbing the kernel from the container image as well as converting the container image into an initRMFS. The second thing that it provides is kexec booting. How many people are familiar with kexec here? Okay, we've got a few. So kexec, it was designed as a recovery mode for the Linux kernel. Basically, the idea is that you can load, you've got your Linux kernel up and running, and you can load a backup Linux kernel into memory, and it's sitting there waiting to go. And when your primary kernel crashes, it can jump into the secondary kernel, and now you can be able to do debugging or keep the system running or whatever the case may be. And so kexec is an interesting tool that we can actually use. So Wyrcan is both a binary, but it's also that binary plus a very small operating system, which includes a Linux kernel. And so first we boot the Wyrcan Linux kernel that's in the Wyrcan image. We download the container, do all of that stuff, prepare the initRMFS, and then we do a kexec pivot into the new kernel. So you actually, as part of your booting, you're going to boot the Linux kernel twice, the first time for the bootloader, and then the second time from the kernel that's been extracted from the container. The third thing that Wyrcan provides is config persistence. So we did need to have some way to persist some information about that particular deployment. So when you're actually deploying a container on bare metal hardware, for example, some clouds have fairly sophisticated networking setups. Maybe DHCP doesn't work at all, and you have to set up bonding and static IPs that are associated with that particular server. Now, because we have a goal for Wyrcan to be stateless, we can't just install an operating system and then configure it all. So we needed some way to be able to persist that configuration across reboots. And so the way that we do this is Wyrcan takes that local state and persists it in EFI variables. So basically, the first time you boot the system, you're going to have to set it up, for whatever it's networking, whatever the needs are, tell it which container to boot. Once you have it all working, then you save that config into EFI, and from that point on, that server is just going to boot automatically. The last thing that it does is network setup. And I've already hinted to this, that on different clouds you have different networking scenarios. Some will just have it working with DHCP. Some will use IPv6 Slack. Others will just have static configuration. You're expected to set up things like bonding and your IP addresses manually. And so Wyrcan also provides the ability to take that networking setup from EFI and then actually set up that network inside the Wyrcan as it boots. And so this is what it actually looks like to prepare a bootable container. If you've ever used a Docker file, that's exactly what this is. Basically, the top just says, we're going to take in an argument which is called tag, and this is just so that we can iteratively build this on multiple releases of Debian. And we're going to say from Debian. So we're just going to choose to base this on top of the core Debian image. And then we're going to do the next step, which is to install the packages we need in order to get it working. So the first thing we're going to do is we're going to update the metadata with apt, and then we're going to upgrade all of the existing packages that are there. So now we have the freshest base repo. Then we're going to install initRMFS tools. And the reason for this is actually surprising. The reason is that if we don't install initRMFS tools, it will be installed as a dependency of systemd and the kernel, which we're going to install next. And the problem is we actually don't want to to generate an initRMFS, because the whole image, the whole container image, is going to be the initRMFS. And so that can easily double, if you're building a small container, for example, generating the initRMFS can easily double the size of the container image. So all we're doing here is we're installing initRMFS tools, and then we are linking over the initRMFS process with bin true. And what this will do is that whenever the system tries to generate an initRMFS, it will just immediately succeed, and now we don't actually generate an initRMFS. So lastly, we install the kernel, Linux image generic, followed by systemd. And now we have all of the packages available. The last line, by the way, just clears the apt cache so that we don't store that in the container. Makes the container image smaller. So now we have all the packages installed that we need to make a bootable container. We need to do two additional things. The first is that we need to symlink the kernel that we've just installed into the special file name Wyrcan.kernel. And this is just so that Wyrcan knows where to find the image. You may have multiple kernel images installed or so forth, and we didn't want to have to do magical interpretation. So you make the decision, you decide what kernel you want to boot, and just link it into the right place for us. The last thing that you need to do is you need to actually set up systemd to run when the system starts, and you just do that by symlinking the binary to /init. And that's it. We've created a bootable container image. That's really all it took. This is an example for Debian, but we have, I think, 5 or 6 different OS's examples on the GitLab site, so you can go and check them out there. All right, so now we're prepared. We've gotten our party. We're armed for battle. And the question is, are we going to fight the battle? Yes, we're going to fight the battle, so we're going to do the battle for boot. And this is what it would look like to actually boot this thing. The first 2 lines here, curl, all we're doing is downloading the pre-built Wyrcan kernel and inodrd. So all of this is built in a reproducible way on GitLab. So you can see exactly what goes into those images. There's no surprises. The last thing we're going to do is we're going to do direct boot. So if you remember before, I talked about direct boot as one of the options. This is where you basically load the kernel and initRMFS directly. And that's what we're doing. We're using Qemu for this. So we're going to launch Qemu, and we're going to come back to the kernel command line in a moment. But go to the second option, which is the kernel and inodrd. You just see that all we've done is specify the files that we downloaded, and that's the Wyrcan bootloader. The next 3 lines are just basic setup. We're going to enable KVM, and we're going to say we don't want any graphics for this particular image, and that's because we're just going to dump all of the stuff to the terminal and record it that way. And then the last thing is just to set, we want 4 gigs of memory for this VM. So that's pretty straightforward. Now let's go back to the kernel command line. We can provide a command line here, but think about it this way. If Wyrcan is an onion, there's an outer kernel and there's an inner kernel. And so you need to have the ability to pass arguments to the outer kernel, which is the Wyrcan bootloader, but you also need to be able to pass arguments to the inner kernel, which may be different from the outer kernel. Perhaps the outer kernel and the inner kernel will have different hardware support because they're different versions, and maybe the software behaves differently. So all we do in this example, the first thing we do is we just tell it which console to use, which is the serial console, and that's why we disable the no graphic. You can see all of the Wyrcan arguments start with WYR. So WYR-arg. This is passing log level equals 3 to the inner kernel. Right, so anything that you specify as just a normal kernel command line argument here will be passed to the outer kernel. All the Wyrcan arguments, all the things that start with WYR are going to apply to the inner kernel. The last one here is weird.image, which is just the slug to the container that we want to boot. And that's pretty much it. And I'll actually give you a demo of this. So first we're going to open up this shell script, and all this is just a convenient way to put all the same stuff in there. So you see all the same arguments formatted in a slightly different way. And you can see we have the command line as well as the kernel initRD there. And we're just going to run this Qemu image. And so we're now booting the outer kernel in Wyrcan. That's what's happening right now. It's being done silently. And as soon as that kernel boots and the networking comes up, we are going to start, okay, we've already started. Now that we're going to deploy this container, we're downloading that container right now. We're, as I said, stream converting it into an initRMFS. and then finally we are booting it. And so now we are actually booting the inner kernel, which you can see here. And that's it. We've done the whole thing. So, but there's other forms of booting as well. So this is an exact same example. The only difference here is that we're setting up OVMF as our EFI in Qemu, and we're booting an ISO image instead. In this case, we don't have access to set the kernel command line directly. So now we're looking at a little simple bootloader here to give us a menu to type command line stuff. So this is what it would be like if it was on bare hardware and you were booting off an ISO image, maybe from a USB key or whatever. And so we're going to say, there's the Wyrcan argument again, specify the console. We're going to specify the image, which is that Debian image. And the last thing we're going to do is we're going to save these parameters using the EFI equals write command to EFI. And so now that EFI image that we enabled with Qemu when it was being booted has now persisted all of those options that we typed. And so on the next boot, we don't even have to type anything that we did in the first case, because everything has been persisted to EFI. Other than that, it's exactly the same experience as before. We're downloading our container image. We are stream converting it into an inner MFS. And I do have a note here. There's some very, very old, very obscure hardware that if you attempt to write to EFI, it bricks it. And I just wanted to warn people of that fact. But it's very unlikely you'll actually hit that anywhere in production. And so we've written all of the variables now, and we're now booting a second time. So this is the second time of our boot. The only reason I'm editing command line image here is because we have to put stuff over serial console. But all of the other variables are now being pulled from the EFI. And we'll see it again. We scanned, meaning that we found that information from EFI. We've loaded our kernel, and now we're booting the inner kernel. And that's it. Now, keep in mind, the entire operating system is memory resident. Now, doesn't that cost you a lot of memory? Not really. The reason for this is, even if you are deploying a large operating system, if you keep your container image small, yes, it's all going to be memory resident in memory. However, if you're just keeping your container image to the stuff that you use, all of that stuff is going to get loaded from disk into memory anyway, and the operating system is going to cache it. So even if you installed that same exact container image to disk and then booted it normally, you're still going to get roughly the same amount of stuff in memory, plus or minus. So it's not actually super painful. I'll give you a quick overview of the Wyrcan boot arguments, as we saw before. Weird.img tells you which container you want to boot. Weird.arg is any arguments that you want to pass to the inner kernel, and that argument can be specified as many times as you have arguments to pass to the inner kernel. The next one is weird.net, and this one takes a little bit of explaining. So there's a kind option, and then a file, section, and key. And ignore the kind option for a moment. The file section and the key are essentially the structure of an ini file. So if you're familiar with what an ini file looks like, that's exactly what this is. It's the name of a file, there's a section in the file, and then there is a key and a value pair in the ini file. And that's because, surprise, surprise, we're generating an ini file using this argument. And the purpose for this is that it's actually generating the network D configuration. So if you saw before, we installed systemd. Systemd comes bundled with systemd network D, which has a full list of networking operations. You can do very sophisticated networking setups with network D, and so there's really the sky is the limit. And this is a very, very repeatable pattern. Basically, if you say, that if you put these arguments in, it's just going to generate the network D configuration file during its boot, and then network D will start up whatever that networking is when it's booted. So we don't even have to document that for you. As long as you can understand that those things transition to an ini file, just go read the network D man page, and it will tell you more information than you ever wanted to know about networking. The last two boot arguments are the EFI write and EFI clear options. And these allow you to persist whatever changes you've specified to EFI, or conversely clear them if you've done something that's wrong and you can't get it to boot, and you're just stuck in this boot loop. You can specify the clear option. It will clear out all of those options, and then you can try again from scratch. So the most important thing about Wyrcan is that it is also itself a bootable container. The only difference is that Wyrcan is a pre-generated kernel in initramfs. So where normally you boot them on the fly, the kernel in initramfs that you downloaded are just generated ahead of time. And that's the only difference. And so what you're actually seeing here is that we are chain booting Wyrcan. So in other words, we're booting into one version of Wyrcan, and then we're telling it, go boot this other container, where the other container is itself a Wyrcan image. So right now we've loaded the Wyrcan itself as a second bootloader, and we've now chain booted. And so this can be useful, for example, if you were to write Wyrcan into a ROM, for example, where you could then use Wyrcan to chain boot onto a network downloaded Wyrcan, and now you can have updates of the bootloader itself as you're actually doing your boot. And so, yeah, that's it. Now we've chain booted Wyrcan. Now you may be wondering, after all of this, what it feels like. This is what it feels like to use Wyrcan. Anybody Stranger Things fan? Yeah, all right. So that's my talk. Any questions?
If you've got some, hold up your hand so we can have the audience hear it. There might be people.
So how do you track whether or not you've already written EFI to individual devices? Isn't there some opportunity to actually mess things up there?
I'm not quite understanding the question. The question was, how do you keep track of whether you've written the EFI to the devices or not? You can always override. Anything you specify as a boot parameter is going to override what is actually in EFI. So there's always a recovery mode. In terms of whether or not you've written before, it sort of doesn't matter because you could just rewrite again. And it is sort of, the intent of booting Wyrcan, and if you haven't noticed from all the metal puns, we're doing this for bare metal, right? And so the intent here is that you're going to have to be setting up a bare metal system. Even as good as the clouds are today in provisioning bare metal, there is some manual process presumed to be involved. We want that process to be as minimal as possible, and then to rapidly iterate from there on out. So hopefully that answers the question.
Anybody else?
Do you support Kali Linux with this? Okay. Do you support? Sorry, that was loud. Do you support Kali Linux with this?
I haven't tried. You're welcome to try. It's a very simple Docker file recipe. So if there's Kali Linux recipe, Docker files for doing containers with Kali Linux, then install a kernel and make sure you have the right symlinks in place, and it should work. But is Kali Linux systemd based? Yes, okay. Anything that's systemd based is going to be a really easy experience. It starts getting much harder when you get outside of that realm, because then you have to do things like modify handcrafted scripts that has certain assumptions about things. But anything that's systemd is going to work very well.
Anybody else? Okay, I've got a few. I was just curious about using this for the use case of handling edge devices that are unintended. Yep. And wondering if this could be a mechanism to install updatable OS images out there at these edge locations.
Absolutely, and in fact, it would be a great companion to use with Enarx, which is the thing we talked about at the beginning. Enarx, if you think about it this way, draws in the security profile of your application so that when you're deploying that application on the edge, which has a lower security domain than a traditional one, you want that security domain to be as tight as possible around the application. So you write and deploy your application using Enarx, and then you could deploy the operating system on which it runs using Wyrcan, and that's a great pair. You might ask about the security of the host operating system in that case. Well, it mostly doesn't matter. That's the purpose of confidential computing. The idea is to install essentially what is an insecure operating system and then have a secure trusted execution environment within which your app runs. And the only thing that the operating system provides is resource management. So how much memory is the application using, right? Is it balanced effectively with other applications that are running and so forth? But because it's running in a trusted execution environment, the kernel can't see, even in ring 0, you can't see into the memory of that application because it's all guaranteed by the hardware. So yes, it is actually a really nice setup for particularly those purposes.
Follow-up then, aligned with this trusted execution environment, is there any value on that device of spending extra money to put a TPM module or some other module on the physical hardware, or does this take care of the same kinds of problems?
Anything you can do with a TPM, you can also do with a trusted execution environment, and you can do better with a trusted execution environment. With a TPM, you basically just get limited key management as well as secure boot. Secure boot is a great marketing phrase, and what it means is that when you turn on the operating system, all of the components of the operating system are measured throughout the boot process, and at the end result of that, you can perform cryptographic operations using that measurement in the TPM. In the case of confidential computing, the security of that chain doesn't really matter so much, or at least not as much as traditionally it was required to. And so you can deploy applications in a way that's very efficient. They have a much smaller, much tighter security boundary. Any key provisioning, for example, doesn't need to go into the TPM because the application itself is encrypted while it's running. So you can do an attestation to a remote party. You can get in cryptographic keys or generate them internally so that no human ever sees them and get the public key signed by another party with attestation. And then your application can run in this way that's provisioned, but it's a very tight, hardened security boundary.
Got it.
Somebody over here had a question.
Yeah, sorry. This is probably a really stupid fundamental question, but I'm still sort of struggling with containers in general overall, and I'm a security person. Essentially what we're looking at here is just nested containers, right? I mean, this is...
No, there's no actual container involved with this. We're using the container format as a way to package and deliver an operating system that is downloaded over the network, that's network booted essentially. And so it allows us to reuse all of our development infrastructure for preparing our operating system images. When it downloads the container image, it's just a set of tarballs. And then we unpack those tarballs in a very careful way so that it efficiently creates an init ramfs, and then we boot that init ramfs. So once it's booted, there's no more container involved. There's no container runtime, there's no namespaces, there's no container at all. You just have an operating system, but we used the container packaging format in order to efficiently deliver it.
Okay. That's cool.
So, if the operating system, if you're trying to actually boot something, like, again, edge use case, if you're trying to actually boot something that's effectively going to run a single application,
Okay.
how much of the sort of init tooling do I actually need?
So I think it's, if you're just trying to boot a single application,
Yeah, I mean,
yes,
so like the use case that I have is it's actually a device that collects data for sensors.
Sure. If you want to run your own init process on that device and have a single process, there's nothing that stops you from doing so. Okay. So you could completely eliminate the systemd step. Remember when we installed systemd? You could install the kernel, but you could leave systemd completely off of that. You could install your own binary as init, and now it's running as PID1, and that's all you have, right? You don't need any other infrastructure. You probably do need some resources, though, for like when it goes down and when it crashes. That's where systemd starts to become very helpful.
Yeah, well, and you also need the full user space if it's good.
Yep. But if you have a hardware watchdog that can determine if the kernel's crashed and reboot the system, then yeah, go out and go to it to your heart's content.
We've got a couple more in the back, but I'm
Sure,
going to
I think we still have time.
Okay. Follow up to his device access. This might be more of an Enarx question, but at that edge use case, is it okay for this inner OS to get to I/O devices, storage devices, et cetera?
So if you're using Enarx to actually protect your application, then your application is encrypted at runtime, all of its memory pages. There's no way to tamper and look inside. In fact, if you go to enarx.dev/cryptal, we have a hack challenge right now. We're basically challenging anyone to see if they can hack the Enarx system and get at data that's inside. Once you've basically built and deployed your application with Enarx, that's a very tight package, right? And just your application is encrypted using a separate key. That key is governed by the hardware. All of the memory is encrypted or decrypted in the CPU directly by the memory controller. And the operating system has no access to any of that. Your application then runs. Enarx provides transparent encryption for all of your network operations, provides transparent encryption, or at least will in a future release, for all of your disk operations. And so once your application is in the Enarx deployment system, it never comes out unencrypted unless you intentionally do so. And so basically all of the secret material you're used to trying to have to protect in the operating system level, you don't have to try to protect that because you can't actually read into that memory inside of the Enarx keep at all. So we can de-escalate the necessity of having a really tight, like, secure boot image, which is really, really hard to provision. I don't know if you've noticed. We've had TPM devices, going on, it's at least 15 years at this point, and they're still poorly integrated into our systems. And the reason they are is because it's an incredibly fragile system, and one change breaks the entirety of the system. In fact, I've even filed a bug. There's a situation in Fedora where if you install on a Windows device with secure boot, the fact that it reordered the boot process breaks the encrypted drive in Windows, right? That's just how fragile the systems are when you have to depend upon secure boot for this. And so what we're trying to do is we're trying to create a much better system where you can have full general compute available with the same level of hardware protections that you would expect out of a TPM.
Talking specifically about Wyrcan.
Yeah.
You mentioned Edge. You can't say Edge without ARM.
Sure.
Is there any ARM support on the Wyrcan side?
There is no reason it won't support ARM. All the major ARM systems these days are EFI. Everything's built using Rust, which compiles fine to ARM. I haven't actually built it and tested it, but I would absolutely welcome contributions for supporting ARM.
So I was wondering about the kernel. Do you have the kernel config? Like, is it like a standard kernel? Or
It's Debian.
It's Debian's kernel? Okay.
Yeah.
So there's no modifications on top of it?
Yeah, if you can boot the Debian kernel, you can boot Wyrcan.
Okay. Thank you.
Last call. Any other questions?
I just went to the GitLab project. I didn't see any documentation or anything on there. Is there anywhere where we can look up the documentation on?
There's pretty extensive documentation in the README. So if you go to
Oh, maybe I just didn't look at in the right place.
and just scroll
Oh.
down, there's quite a bit
no,
of
it's there.
documentation.
It's
here.
okay. I think I didn't see that because I'm on my phone.
Yeah, no worries.
All right, thank you.
Yeah, I have the same problem too.
Anybody else?
Does this work with Pixie or iPixie?
Yes. Yeah, basically you have the Wyrcan produced kernel and initRMFS. You can boot those any way you want. We also produce from that an ISO image that just boots that kernel and initRMFS. So whether you use the kernel and initRMFS to boot or whether you use the ISO image to boot, you can configure it any way you want on your hardware and it'll work. So using Pixie, for example, Pixie just fetches the kernel and initRMFS from TFTP over the network. So just put the Wyrcan kernel and MFS on your TFTP server, and there you go, it's booted.
Any others? Okay, well, I want to thank Nathaniel. This has been a great talk.
Thanks for having me.
Let's give him a round of applause.
Safe journey home, everybody.